Good afternoon, my fabulous chemistry minions.
Unit 11 organic vocab video today.
Who you?
I'm MoNaCo.
Oh,
Come on.
I know. And I'm Milks, but hey, here we go. Video number 2.
Page 3 and 4 in your pack. Testable vocabulary.
Shall we do it?
We shall.
It's going to be a little bit different than all of our vocabulary videos previously.
Oh, yes, it is.
Would you
I
like to-
remember, we got pictures this time.
Yeah.
So
Pictures
this
and
is
definitions.
a learning lecture vocabulary. So let's start with the top.
Okay, first one.
Homologous series.
Table Q.
This is what it looks like, and this is the definition of a homologous series. Group of hydrocarbons with similar chemical formulas. So they all look almost identical. If you were not careful, you would get them mixed up.
Right, we'll learn the difference.
Hence, we teach you the difference to see table Q.
Correct.
Moving forward.
Organic prefixes. Notice table P. Different prefixes. They're going to help us in our naming structure.
For numbers of carbons, I saw the
Correct.
relationship there. So
Here it
prefix
is.
versus carbons.
The words that tell you how many carbons that form the carbon backbone
of
of the molecule. See table P.
Very important in nomenclature.
Okay.
Functional groups. These are the sore thumbs, if you will, that stick out on organic molecules. They are not made of carbon and hydrogen. They are oxygen, nitrogen, maybe a halogen in place there. These make organic molecules have a different function. That's why we call them a functional group. There it is. It's a part of the molecule that makes it different from plain hydrocarbons based on the number of nitrogens, oxygens, table R. Look it up.
Alkanes. Here's an example. Methane, ethane, propane.
I recognize those prefixes.
From the last one,
Mm-hmm.
or 2 ago. And specifically, alkanes are a group of hydrocarbons that contain only single bonds between their carbons.
Which was the single line that you just saw between
Correct.
the carbon atoms.
We did learn a lot about that back in bonding.
Here's some alkenes that contain a double line or a double bond between carbons. Notice it changes the names. Hydrocarbons that contain at least one double bond between the carbons. That's it.
Okay, and then the next set
Alkynes.
would be the alkynes. Notice in these there are triple bonds, at least one, maybe more.
And
So
the names are going to reflect that.
True, they will, and we will get into that. So this is now hydrocarbons that contain at least one triple bond between their carbons, and that would be an alkyne.
Structural formulas, you've been seeing them all along. It's basically the shape, the picture of the molecule. Diagram representing the number and arrangement of the atoms. Carbons connected to what on all four sides?
See, that's extra information, because not only does it give you the number, it gives you the arrangements in space.
Which helps a lot.
Right now, molecular formulas, when you see here, you've seen this a lot too,
Tons.
it tells me how many carbons, how many hydrogens, but it doesn't give me that information about where they are in relation. So now it's just a symbol that shows me how many of each, not necessarily where they are.
Correct. Isomer, root or prefix iso, kind of like isotope, but isomers
Same.
are, isotopes are to atoms as isomers are to organic molecules, because it's two molecules that have the same number of each type of atom, but they're in a different arrangement. The puzzle pieces went together slightly differently.
Correct. Of course. Now, the name's going to be different, and the function's going to be different.
It will behave different. It's different molecule.
Correct.
Even though it had the same
Correct.
formula, the way they go together matters.
Right. Straight chain. So
There.
notice these carbons are all in a straight line, and this is a simple hydrocarbon chain that has no side chains or functional groups, nothing setting it apart, kind of ordinary.
This
kind
is
of plain.
going to be the main focus at first, so you're learning the
Might as well
nomenclature.
start simple, right?
You gotta
And
start
then,
simple.
Then we'll start getting a little bit more complicated.
Cool. A branched hydrocarbon. So we've figured out our simple straight chains. Look at these. These straight chains of hydrocarbons have carbons hanging off the middle of their chain, which changes the names, changes the function. It has one or more carbons attached to the side, not just a straight chain anymore.
Right.
Period.
Okay, so kind of using probability here.
Mhm.
Saturated. So these are going to be, fairly straight chain things, and notice that all the carbons are full.
Right.
Basically, they are holding as much hydrogen as they can.
Great.
Specifically, alkanes. If I'm single bonded, all my spare bonds can hold up hydrogen, and I'm saturated.
All alkanes are saturated. Unsaturated hydrocarbons could belong to the alkenes or alkynes family because the carbons are occupied bonding to other carbons. They're not full of hydrogens. So a hydrocarbon that does not hold as many hydrogen atoms that it could. So just the alkenes and alkynes class of compounds are unsaturated.
Okay. Monomer is like a single unit.
Right.
It's like a building block or a Lego.
One link in a chain link fence.
Correct. So it's a molecule that can combine with very many of itself to form this big, long polymer. And remember, poly is many.
Right. So a chain necklace is in some ways a polymer. Each little circle is one monomer.
Right.
Put 1,000 of them together, you've got a chain.
That's a great analogy. And then specifically,
polymerization reaction is the process of linking many monomers together to make a large chain. There's a few different ways to show this with the notation with parentheses and dots, because if your chain is 1,000,000 units long, I can't fit that on my paper.
right, N will work.
N works. So we have a special way to show polymers on paper because they just go on for like ever sometimes.
Yeah, it's kind of neat. Kodak was really good at making polymers. We were fun with that.
Yeah.
Fermentation. This is one of my personal favorite reactions. I wonder why.
Humanity's favorite reaction.
Seriously.
It's one of the reasons why we've been able to become technologically advanced. Back in the day, you could not drink the water. You would get sick and die.
Seriously.
Making
so this
alcohol.
is a reaction where an enzyme reacts specifically with a sugar to make alcohol as a product.
Once humans figured this out, human technology and science and longevity increased because you didn't just drink the water down in the puddle out of the pool.
That was
and
a problem.
You would die, so you couldn't pass on your
Right.
knowledge and genetics. But
This is your favorite.
my favorite combustion reaction. This is where a hydrocarbon burns in the presence of oxygen, making CO2 and H2O. The two products of any combustion are always carbon dioxide and water.
And you're always looking on the reactant side specifically for,
A hydrocarbon and O2.
well, the O2 is the key.
O2,
word.
you gotta have it.
Gotta have it. Saponification, that's right. It is, if you didn't know, making soap. Specifically, I'm going to take a base, react it with a fat, and I'm going to make soap.
Another really important
Number one-
reaction to human
Seriously,
survival
Number one rule of Fight Club.
is you don't talk about Fight Club. But esterification. So this is important because we like to use polymers and esters. One of the first polymers was called polyester. It was an esterification reaction between an organic acid and an alcohol. Made these long fibers before World War II, I think. It basically made parachutes possible at that time. It was one of the first applications. And nylon stockings.
Sure. And now, they also, a lot of the esters smell real pretty. You can put them in perfumes and stuff.
Yep, certain ones. So this was a really cool set of reactions.
All right, so here's a substitution reaction. If you look at it real carefully, you can see that the H and the Cl on the product side have swapped. I've substituted them. So the reaction goes where an atom of one molecule switches with an atom of another molecule in the end of the reaction.
Substitution reactions, we don't say much about them this year at all, except that they are the great initiators. If you want to make a really long, complex molecule like a pharmaceutical drug or something like that, you start out with a substitution reaction because it puts a functional group on your straight chain where you want it, and then you can start building up the molecule, and eventually you get, a cholesterol drug or a headache medicine.
Okay.
An addition reaction is really important for breaking double bonds and making saturating things. You can do addition reactions with H2 or Cl2 or bromines and all that other stuff. It's a reaction where an atom of one molecule is simply added to another molecule across the double bond. We have to have that double bond in there for the addition reaction.
Otherwise, it ends up substituting.
If you were to use hydrogen as the compound that you're adding to, it would be called a hydrogenation reaction. You might see hydrogenated soybean oil on your food. They do an addition reaction to stabilize that fat and that oil so that it lasts longer on the shelf, makes creamier peanut butter or whatever it may be.
Nice.
Better living through chemistry.
Hey, these are the words you got to know for sure. We'll be using them over and over again.
Yeah.
Get ready, study up, take your quiz. Let's go.
See ya.